Okay. Good morning, everybody. So I've been told that I should not write on this side, so I will just write a little bit on this side, let's say. Uh, I had a very general title. I don't remember what it was, physics and machine learning or something like that. So, but I decided to focus on one rather specific topic, which is statistical physics of generative diffusions. So why did I pick up this topic? For several reasons. First of all, it's fun. It's a hot topic in machine learning. I think that, well, you have all read, heard, and played with generative models of all kinds for generating images or text, and so it's one of the really important developments of recent, of modern time machine learning. It's also one which was probably not so much, even if there are precursors, but it was not present in, for instance, in the 90s. You know, in the 90s there was a big boom on machine learning, but it did not really deliver in terms of practical application. And when machine learning started again in 2012, it was about image analysis, etc. And all the tools, basically all the tools, were already present 25 years before. But since then, there have been quite new things. And one of the new things has been the development of generative models of all kinds. There are many kinds of generative models. So this idea that it's interesting to generate new data. You have existing data and you want to generate new fake data similar to, in some sense, the one that you already have. To me, it is also an interesting question for two other reasons. First of all, it is deeply related to statistical physics, and I like statistical physics. And thirdly, I think that the main challenge for statistical physics in machine learning at the moment is to be able to develop structured data ensembles of data with a lot of structure, which traditionally all the approaches of physics in machine learning, if you think of learning in a perceptron, learning in a two-layer system, etc., they were addressing relatively simple systems in which you may have a teacher, the teacher may be a bit sophisticated, a teacher and a student. Does the student succeed in learning the rule given by the teacher? But it was all based on very simple data model, very often just IID data. And so I think that one of the main horizons is if we want statistical physics to have an impact, it has to be able to understand, to analyze structured data. And structured data, there is nothing better than a generative model. The generative model gives you a model in which you understand all the steps of the model that will generate data for you. And so it's a very good way to analyze the structure of the data. So that's why I want to learn all that. So Eric yesterday gave a wonderful lecture in which he already discussed quite a few of these ideas. I was hesitating a little bit what to do, but I decided to redo it in some sense in my way. I think learning, it's always a good way of learning is to see an object by different points of view, different perspectives. And I think that you will have a slightly different perspective, and maybe in the end, the whole shape of the object will make sense for you. So that's, and maybe I want to illustrate that because I picked up the sentence of Eric yesterday. At some point he said, I want to use machine learning in order to analyze systems in large dimensions. And let me just propose my point of view, which is I want to use large dimensions in order to analyze machine learning. And more specifically, I want to use the simplifications that occur in the limit of large dimension, and that is, when we speak of probability distribution in large dimension, that is really what statistical physics is about, trying to, make use of the large dimensional limit in order to analyze and especially identify mechanisms. I think that what physics can bring to this field, it's a field which is enormous. It's blossoming in all directions. There are tens of thousands of researchers working on that in all fields, mostly on application. But what physics can bring on the theory side is trying to identify some mechanisms, some general principles which are at work. And that's what I want to try to do. And I think that for this generative diffusion in these 2 mornings of lecture, it should be possible to go to do that with you. The technical level there is nothing much technical in all that. It's relatively simple. So I will try to do it, to do my best to keep everybody on board. I will try to always start by simple examples and only then go to the kind of more general situation. So the first, I have 8 chapters. Let me mention the first few. I will start by really a very fast introduction to Langevin, Fokker-Planck, Ornstein-Uhlenbeck processes. Then I will develop the general principles of generative diffusion. I will study the simple case of Gaussian data. And then I will try to mention the related approaches, some of the related approaches. And tomorrow I will go to various types of phase transitions and dynamical phase transitions in this system. So the first chapter is very short. It's just probably to define the notation that I will be using and be sure that everybody is on board. So I will start with the Langevin equation. So take one particle in one dimension, and the Langevin equation is an evolution equation, x of time. The derivative of x is equal to some force plus some noise eta of t, and eta is a Gaussian process. It's defined by its first moment. The first moment, eta of t, is equal to 0. And the second moment, eta of t prime, is equal to 2 delta of t minus t prime. The 2 here is the same square root of 2 that had Eric yesterday. It's there to simplify the next formulas. It's a bit strange when it appears here. That is, by the way, exactly what was written yesterday by Eric, I think, in the form dxt equal something that I think he called it B, but it's, well, I'll call it F, plus a Wiener process, maybe with the square root of 2 dWt. So this is the same as that. Okay? Just dt. Thank you. Okay. So this Langevin equation, it will be important. I mean, all this will, in the end, it will turn into algorithms. I mean, we'll define algorithms that are able to generate new images, etc., etc. So you have to be able to run the algorithms. So running the algorithms means that you have to be able to discretize that. And so the standard discretization that I will use is the Ito discretization, in which I will write x of t plus delta t is minus x of t is equal to f of x of t delta t plus a noise. What is this noise? Here I have to be a little bit careful because I have a Brownian noise here. I have white noise which is delta correlated, so it oscillates infinitely. So I have to take into account here something which is the integral from t to t plus delta t eta of tau d tau. This guy oscillates, even if I take a small delta t for my simulation, this guy oscillates a lot. But this is a Gaussian variable. Let us call it, I don't know, z of t. Let us call it z. It has mean 0. And d square, well, I have to take the double integral, take the delta function correlation, which is here. And I find that d square is equal to 2 delta t. Okay. So basically, my discretization will be that I do steps of size delta t, and I find x of t plus delta t minus x of t is equal to f of x of t delta t plus z, and this z normal distribution of mean 0 and variance 2 delta t. Okay, so with that you can simulate your Langevin equation. Is it? Please, you don't hesitate to interrupt me. So, Fokker-Planck equation, if we call Pt of x the probability density of the particle at point x at time t, we can look at the evolution of Pt of x. Is it useful that I do it? It takes me 5 minutes, or you have seen already many times. Giulio says it's not useful. You agree with Giulio, or someone wants to see it? I don't, when I say that, I don't know how to interpret. Who wants to see the proof? Okay, okay. Well, there are more people than what. Okay, good. Then the trick is to use a test function. So you take a function g of x, which is regular enough. I'm sorry, I will not write all the conditions of differentiability, etc., etc. I always play with functions which are regular enough. Otherwise, when I set it, and let us look at the average of g of x at time t, which is equal to the integral dx pt of x g of x. And let us follow a trajectory. So what we are looking at g of xt. We look at the evolution of g along a trajectory, and we see how it evolves. So how it evolves, if I change my time a little bit, I will change my x a little bit, and I will have to follow the change of g. So what will be the change of g? Delta g will be dg dx delta x plus 1/2 d2g dx square delta x square. So here is a small trick. The only point on which one has to be careful is that when you look at the evolution of a function of x, you see that I have decided to go to second order. Why did I go to second order? Because delta x has a piece which is of order delta t, and a piece which is of order square root of delta t. This guy is of order square root of delta t times a normalized Gaussian. So delta x square also has a piece of order delta t. Okay. So now I insert here what is delta x, and I find that the expectation value of delta g will be equal to dg dx times the deterministic part of the evolution of x, which is f of x delta t, plus 1/2 d2g dx square. And here I have the second piece, which is the z squared average, and which gives me a 2 delta t. Okay, so this tells me that I can compute dg dt. Okay, and sorry, this should be the expectation value over x. And so this is equal, for on the one hand, it is equal to integral dx dpt dt g of x. And it's also equal to integral dx p of x times dg dx f plus d2g dx square. And now what I will do is I do integration by parts. So this dg dx, this piece here, I can rewrite it as integral dx. The first piece here, I do dg dx, I do integral by parts. So it's g of x times minus d dx of p times f. And then I will have plus d2p dx square. The second piece I do twice the integration by parts, and I assume that my probability density goes to 0 at infinity, so there is no boundary term. I can do safely the integration by part. And so if I identify these two formulas here, I find the Fokker-Planck equation, which is dp dt is equal to, let me write it, d2p dx square minus d dx of f of x times p. Okay, you can do that. So here I was yeah, I never go there for something important. It's just I should move in parentheses. I should have written that on the other side of the mistakes. I will try to put them on the other sides. But I do my best. Not to avoid mistake, but to hide them. Okay. So it means that it's okay. This remark shows that it is okay. You can do that in a higher dimension. You can do the same thing for x belonging to r to the d. Okay, let me write the equation here. So here I have generalized to the fact that x is a vector in r to the d. Okay, and the second derivative becomes a Laplacian, and this is the divergence of the probability times the force. The force is also a vector in r to the d. Okay, so I don't write. Okay. You have to infer from what is the object that this is a scalar, this is a vector, this is a divergence. Okay, that's all. This means that. Okay? Good. The simple case in which f is the gradient, is minus the gradient of a certain potential, V. Then you can find what is the stationary solutions. You solve the equation dpt dx, dpt dt is equal to 0, and you find that pt of x is equal to e to the minus v of x. So you find a Boltzmann distribution with temperature units equal to 1. Okay, that's the reason for my famous 2 in the correlation of the eta. It is to be sure that I find unit temperature in the end. Good. So let me see a simple process here, which is the Ornstein-Uhlenbeck process. Okay, Ornstein-Uhlenbeck is a very simple case. It's a case in which the potential V is x squared over 2. Okay, I mean norm of x square over 2. Maybe I will not always write the, this I will also write it as x squared over 2. I will use a kind of simpler notations. So it means that the Langevin equation is x dot equal minus x plus eta of t. And it is a very simple process. I will. The reason why I'm spending time that it will be the basic process that we will use for generative diffusion. Actually, it turns out that the simplest process one can imagine is the one that is useful. So this equation, it's a linear equation, so you can solve it easily. You will find that if you start from initial condition x of 0, let me call it a. So this is always in r to the d. Then you will find that the solution to this equation is x of t is equal to a e to the minus t plus integral 0 to t of d tau e to the minus t minus tau eta of tau. Okay, that's just standard solution of a first order differential equation. You can just check when you take the derivative, you have the derivative with respect to t here and t here, and this gives you the minus x. And the derivative with respect to the time, which is here, gives you eta of t. And it has the right boundary condition at time 0. So what does the Ornstein-Uhlenbeck process do? First of all, I need to look at this random variable here. So this random variable is, let me call it u. So this is a sum of Gaussians, so it is a Gaussian random variable. I just need to compute its first 2 moments. Mean of u is 0 because the mean of eta is equal to 0, and mean of u squared is integral 0 to t d tau, integral 0 to t d tau prime, e to the minus 2t minus tau prime, times the correlation function of eta of tau prime, and this is 2 delta of tau minus tau prime. So this gives me altogether, you work it out, it's a simple integral. This gives me 1 minus e to the minus 2t. and this I will use a lot. This is the variance of this random variable. So I will write that x of t is equal to a e to the minus t plus z square root of delta, and delta is 1 minus e to the minus 2t. Is it okay? Yes? So what is it doing? It is doing the following thing. Let me draw it in one dimension. This is x, and this is time. And I start from a certain point A. And basically what I will have is I have a trajectory, which is a stochastic trajectory. It has some noise in it. But the mean is just a e to the minus t. And then what happens is that at the beginning, at small time, delta at small time is very small. You see, it's of order t. So you have a little bit of noise. Then the noise increases. And then when you reach the long times, this is equal to 1. And you get a process which here the mean has decayed to 0. And it is pure noise of width equal to 1. So you get something which does something like that. I'm not very good at drawing pure noise, but that will be it. Okay. And what we find is that if we are at large time, let's say that we look at TF final time much larger than 1. Well, what we know is that we will have a statistics of arrival point, depending, you can generate many trajectories. You look at the statistics of arrival point, and you find that the distribution is a Gaussian, because the final for TF much larger than 1, PTF of x is equal to e to the minus x squared over 2, normalized. It's just a Gaussian. Here I draw it in one dimension, but the same is true in any dimension. Okay, so this will be important actually. It's very simple, again, it's the simplest stochastic process one can work with, but it will be important. We will use it quite a lot. A couple of comments maybe before moving to real things. There is one comment I want to make. Also one thing that I forgot to say, I did not produce lecture notes. Okay, I might if I find some help. So if there are someone who is volunteer or groups or whatever, then we might think of doing something. Otherwise, you can write your lecture notes. And one thing that I want to mention here is the possibility of time reparametrization. So there are several ways you can reparameterize time, but a natural one is to look at an equation of evolution. In my Langevin equation, I always start from the Langevin equation. I could write it in a more general time schedule like that. Minus 1/2 beta of t x plus square root of beta of t eta of t. And here I would take eta of t prime equal to delta of t minus t prime. So the factor 2 that was here, it has been transferred there. So a simple exercise is to now you can always solve this equation completely, linear equation in time. You find that the general solution is x of t is equal to a, the initial condition, e to the minus 1/2 integral 0 to t beta of tau d tau, plus an integral 0 to t dt prime, square root of beta of t prime, e to the minus 1/2 integral t prime to t beta of tau d tau times eta of t prime. So this is a general solution of my linear Langevin equation. It has a deterministic part. You see, you recognize in the usual case we had beta equal 2, and a was a e to the minus t that you have here. That's a generalization. And now the noise, it's always a Gaussian noise. So it's a linear superposition of a Gaussian noise. So the only thing that you have to do here is to compute the variance of this noise. And the variance, so this is x of t is equal to and you find that the variance now has become 1 minus exponential minus integral 0 to t of beta of tau d tau. So x of t can really be written as a times square root of 1 minus the variance plus a noise times square root of the variance, and the noise here, zt, is a Gaussian random variable of mean 0 and a unit covariance matrix. So this may be useful in many cases because people tend to use for generative diffusion different schedules, which are not exactly the one that I started with the exponential. My schedule is a beta equal 2, and I will keep with my schedule because I like it. But then if you want to program it or you look at the papers, you will find that people use different schedules. Not always innocuous, actually. Okay. So this is the first chapter. Are there questions? Okay, let us now go to the heart of the topic. And this is chapter 2. The principles of generative diffusion. Okay, so I can send you references. I mean, what I will talk about is something that has mostly evolved in the last 4 years, basically. It's relatively recent things. There were some precursors. There was a paper by Soldigstein, Weiss, Maeswaranathan, and Surya in 2015, which gave already, I mean, it was setting the stage for all that. There was an important paper by Yang Song and Stefano Hermon in 2019. And there are already quite some reviews. One review that you could look at if you want to have also all the reference, etc., would be the paper by Ling, Yang, et al. which is on archive with the number 2209.00796. This has a lot of the, I mean, I should say that even before going to the related approaches, which will not be generative diffusion, just at the level of generative diffusion, there are a lot of variants. You know, you can look at it in continuous time, in discrete time. You can, there are various time schedules. You will find a lot of variants in the literature. I take one path. I think that basically for what I want to do is to give you the ideas, how it works, etc. Once you have one path, it's relatively easy because you can connect to all the others. So the idea of generative diffusion is a sequence of a forward process and a backward process. So, so the idea, let me first describe the forward process. So you will, the idea is that you start at time t equals 0, and you generate data according to a certain probability distribution P0. Okay, so that's my initial data A. And then you will take a data point and you will degrade it by adding noise through a Ornstein-Uhlenbeck process. And as we saw when we follow the Ornstein-Uhlenbeck process, you remember this plot that we had. We were following the Ornstein-Uhlenbeck. We start from A, and we have the mean, which does like this. And then we have a little bit of noise at the beginning, then the noise amplifies, and then you have a noise of variance 1. Okay, so we will do that, and then we will arrive at pure noise, and then we will find a way to go backward. And so the way it is used really is by using as P0 a database. I mean, it's mostly used in practice. I mean, we will also study cases in which we know the P0 because we want to understand how to generate new points from the P0. But in practice, you have the P0 which is given by examples. That will be an empirical P0, let's say. And so you will be able, let's say, take images and you will degrade them. So I will not show, maybe in the last part, in the last talk, I will show a few images because, but you have seen the images of celebrities, etc. So just not to be disturbed, I will draw the images, so they will not be disturbed by the celebrities. So you start from an image. Okay, that's an image, and you have a database of images like that. And then what you do is that pixel by pixel, so that might be d-dimensional images. So you have x, which is in R to the d. X gives you the intensity. Let's say that there is a single color. It's a gray image. So x is the intensity of gray on each pixel. And what you will do is add noise to all this. And so you will have some you'll see that after some time, and then after a lot of time, you find that. Okay. So we do exactly what I was describing before. We run the Fokker-Planck equation. X dot is equal to minus x plus eta. And we run it component by component independently. So it's a very simple process. That's one of the advantage of the, I mean, yeah, I promised I will keep to the simplest case. So I will keep to the simplest case of the Ornstein-Uhlenbeck. One of the simplifications that occur in Ornstein-Uhlenbeck is that the force Fi of x is just minus xi. It does not depend on the other components because it's a Gaussian. It's a gradient of a Gaussian. And so the equations decouple. So basically you have a trajectory like this for each pixel. So we do that. We have already done all of the work. So we know what is the probability pt of x, and we know that it satisfies the Fokker-Planck equation. So it satisfies dpt dt is equal to Laplacian of pt plus the divergence of x times pt. Okay? This is a scalar, this is a d-dimensional vector, this is a d-dimensional divergence. So what is pt of x is equal to integral dA p0 of a times e to the minus x minus a e to the minus t squared over 2 delta t, normalized properly to square root of 2 pi delta t to the power d, and delta t is the variance of the noise at time t, and we have computed it before. This is 1 minus e to the minus 2t. So you remember, when we follow this process at a time t, the mean is a e to the minus t, and then there is noise around that, which has a variance delta t. This is exactly what is expressed here. Okay? This is what we have derived before. So we know everything about this process. By the way, I will probably have to use quite a lot of these normalized Gaussian. I will write that as the Gaussian distribution for the variable x with mean a e to the minus t and variance delta t, Gaussian density. So I find that pt of x is equal to integral dA p0 of a times the Gaussian x a e to the minus t delta t. Okay, so this is the forward process is basically what we had been doing before. So we know all that. Now I will look at the backward process. So the backward process is where a kind of miracle appears. The backward process is starting at very large time, pure noise, and going backward in time and generating an image of a cat. And hopefully an image of a cat that you have never seen before, which is one of the main topic of what I will be talking about, which is a question of collapse, but we will see that. First of all, let us imagine that we have a certain P0 of A, and we have evolved the forward process up to very long time, so we take TF much larger than 1. Actually, you see that everything decays exponentially in time, so in practice, if you take time equal 10, you're done. I mean, you have completely forgotten about the initial condition. So it's not a very stringent condition. So we start there. We have PTF of x is equal to e to the minus x squared over 2. And now what we will do is reverse time. So imagine that I am at time tf. I have chosen it large enough. And then what I will do is that I will reverse time, and I will count time from tf backwards. So I introduce t, I write it as tf minus tau. And tau equals 0 means the beginning of my backward process. Okay, that's that. Let me write it because it will be important. I will always use that. So tau equals 0, it means t equal tf. It is the beginning of the backward process. It's the end of the forward process and the beginning of the backward process. tau equal tf, t equals 0, it is the end of the backward process. Okay? And let us look at our Fokker-Planck equation. So we had the forward Fokker-Planck. It was written as dp dt is equal to Laplacian of p plus divergence of x times p. And now, if I reverse time, I will find that dp d tau is equal to minus Laplacian p minus divergence of x times p. Okay. Just change the sign of the derivative. Now, the trick is to find a Langevin backward process. So what will be this Langevin backward process? It will be an evolution of the particle backward, dx d tau. So now I have my trajectory. I started from a Gaussian distribution. I started from this point here, and I start to evolve it with a Gaussian, with a Langevin motion. And the Langevin motion is it will be written as a certain force which depends on x and on time plus eta of tau. Sorry, when I say eta, it's always a generic eta. It's not the same as the forward. It's each time it's a new Gaussian. I have a very big factory of Gaussian random numbers, so I can generate as many as I want. What we will find is the force here that is such that the Fokker-Planck equation associated with that is the reverse. So how do we do that? Well, it's very easy to do. Let me give you the result and we will check it. If we find that if we use the fact that f of x tau is equal to x plus 2 gradient of the log of the probability, then here we have a Langevin equation with a certain force. I can write the Fokker-Planck equation for this thing here. The Fokker-Planck equation is dp d tau is equal to Laplacian of p minus minus the divergence of f of x tau times p. And so this will be Laplacian of p minus divergence of x times p, which comes from these terms. And then I will have minus 2. And I use the gradient of log p is gradient of p over p. Gradient of p over p multiplied by p. This is gradient of p. Divergence of gradient of p gives me a Laplacian. So I get minus 2 Laplacian of p. And this is equal to that. Okay, so this is what Eric was showing you yesterday. So what we have is a way to invert time in the Fokker-Planck equation and to realize that in an auxiliary Langevin process. This auxiliary Langevin process, it has a force which is the force that we have written here, f of x and tau. It's a time-dependent force, which is equal to plus x plus, I will write it 2 s of x and tau. And s of x and tau is a gradient of log p computed at time tf minus tau at point x. and this is the score. Okay, so everything is explicit. We have a backward Langevin process. It is a bit strange because it has the reverse potential. You know, this would be like a flow in a potential which is reversed. Instead of having a confining potential x square, you have a repelling potential minus x square, repelled from the origin. But you have another very important component of the force, which is the score. And now what we have shown, and that's could write it as a theorem. The theorem is that if we start from pure noise at large tau, tau equal TF, we will generate some data distributed according to P0. Actually, we have more than that. We have that at any time. The probability forward of x at time t is equal to the probability backwards of tau equal tf minus t. So not only are we able to step back from pure noise to a cat image, but at every intermediate time, we have the same sampling, the same statistics of the distribution. A small comment on this backward equation. So the backward equation is dx d tau is equal to well, there is one regime in which we can analyze this equation easily. It is this regime which is here. Here we are at time, here I take a TF which is very, very long. So we are at a time where we have completely forgotten the initial condition of the initial process. So we know that in this regime, at a certain time t, which is here, much larger than 1, we know that the p forward of x at times t is more or less Gaussian. Okay. So it means that the score in this regime will be the gradient of this Gaussian. It will be minus x. Okay. So it means that at very large time, what I will have is that s of x tf minus tau will be more or less minus 2x. And so what I have here is a good old Ornstein-Uhlenbeck process. That is dx d tau is minus x plus eta. So it means that in all this region, I forget whether I was looking at a database of cats or students or celebrities. Here, I have noise. And my backward process, although it had this x, which seemed to be an inverted potential, it turns out twice the score builds the right potential. Okay? So why do I say that? I say that because if you take TF in that region, here, well, it means that really what you will have for some time, before you start to see the evolution of the mean, you will have a pure Ornstein-Uhlenbeck. And so what will happen is that, yeah, we insisted that here we sample according to a Gaussian. But in fact, you don't care. You can sample according to whatever you want. You can decide that you start at x equal to 0 if you want. Does not matter. Because there is this whole part of the process which is an Ornstein-Uhlenbeck, and the particle vibrates in its well. And when the things really start to happen, when you will start to have trajectories which will generate the P0 of A, you have completely forgotten this initial condition which is here. So the point where you will arrive at time equals 0, the theorem that we have is that at time t equal to 0, we have, or tau equal x at tau equal tf, or which means t equal to 0, it is distributed according to P0. That is our theorem. But the point where you will arrive, it will depend on the Langevin noise along the trajectory, but it will not depend on the initial condition. Okay. On the other hand, you might also do something else. You are not forced to interrupt at very, very long time. You could do something slightly different. You could decide to interrupt here. And then you still have some structure. You have not yet forgotten the initial condition. It's still valid what we did, provided here we sample with the right evolved condition. If we sample the initial condition at time, we decide to have TF here, then at time TF we have the P forward at TF of X. If we sample from that and then run backward, the theorem still applies. But it is crucial that you sample from the right thing. And now it will depend on the initial condition. Okay. Is it okay? Well, you know everything now, so the rest is comments. Let me talk a little bit of discretization. So the way I will use it for simulations, etc., will be to discretize the Langevin equations, both the forward and the backward, using the Ito convention, exactly as I showed you at the beginning of the lecture. Okay, but it's interesting to have a look at slightly more general processes, which could be discrete processes, let's say. Imagine that you look at my process. You start from time t equals 0, x0 equal a, generated according to some initial probability distribution. And let us discretize the time t in units of some small time delta t, small increment delta t. So what we have seen is that if I write xn equal x of t equal n delta t, what we have seen before is that the Langevin equation, properly discretized, reads now xn plus 1 minus xn is equal to minus xn delta t plus eta n square root of 2 delta t. And this eta n has variance 1. Actually, we are in d dimension here. So the probability distribution of the forward process, I have a forward process that takes me it's a Markov chain. It takes me from an xn to a xn plus 1. And In our case, we know what it is. This is just, let's say, a Gaussian G. I don't remember how you wrote it before. G, maybe like that, of xn plus 1, with a mean which is xn 1 minus delta t. I read it from here, and a variance which is 2 delta t. And basically, I can look at my probability, my forward probability of the whole chain. So I can look at the whole chain. The whole chain is x0 to n. So it is the whole sequence, x0, x1, to capital N, after n time steps. And this will be p0 of x0 times the forward probability x0 goes to x1, x1 goes to x2, xn minus 1 goes to xn. So we have a Markov chain. We can identify what is the probability of xn plus 1, and that will be sum over xn of the probability of xn times the transition probability from xn to xn plus 1. Very simple general process. Write it this way because, I mean, this is just, in our case, a rewriting of what we have been doing in discrete time. But then you could also want to generalize the process in something that would not be necessarily the Gaussian process, that would be something more general. And that formalism would be helpful. So this was the forward, and then we will look at the backward. Well, we can look at our backward Langevin equation. Xn minus 1 minus xn will be equal to minus xn plus twice the score at xn delta t plus eta n square root of delta t. And so I have a hopping probability backwards that brings me from xn to xn minus 1. And in our case, it is equal to a Gaussian of, it's a Gaussian distribution for xn minus 1 of mean xn 1 minus delta t minus 2 s of xn delta t, and on variance 2 delta t. And the total probability of the backward trajectory, the one that goes from x capital N to xn minus 1, etc., to x0, will be equal to well, what it has to be, p backward, how I reach x0 from x1, how I reach x1 from x2, how I reach xn minus 1 from xn, and then I had the p final of xn. A minus in what equation? This one here? You say the plus x here? Maybe you're right. Now yeah, that's, thanks a lot. Now I have, previously I was using tau, which is t f minus t, okay? So if I would use new indices for the backward, which would be, I don't know, n prime, which is capital N minus n, then I would have to change the sign. But written like that, it's like this. Merci. So now imagine that, so this is my final. In the backward process, I start from a final P of xn, and then I iterate the backward process. Okay? So now, if you have these two conditions which are met, that is, if I have the P forward of xn, and this will be the P backward of xn. And the second condition is for all n, P forward of xn minus 1 times the P forward of the transition from xn minus 1 to xn is equal to P backward of xn times the transition from xn to xn minus 1. So this condition tells me I have evolved long enough and I start from an initial condition which is the final distribution for the forward process. And the second one is a kind of detail balance condition. Tells you that the probability distribution on the forward, when you push it one step right, or you take the probability distribution from the backward and you push it one step left, you have the balance. Okay. So if these two conditions are met, then it's just looking at this and looking at that, you can show that the probability distribution of the forward is equal to the probability distribution of the backward. I don't do the proof, but it's just by recursion, basically, using this. I mean, you absorb it by recursion. So this is something that I will not, it's just a parenthesis. I don't want to go much in that direction. But I mean, there is, if you read in the literature, a fraction of the papers on generative diffusion are actually using more this kind of formalism, which is discrete formalism, with these processes of the backward and forward and backward jump, which satisfy this kind of condition. And the whole trick of denoising will be, to have a good approximation of that process, of that detailed balance. I have several questions. Yes. Yes. Yes, certainly. If you go to long enough time, yes, you can start from deterministic if you want. This will be important when I go to chapter 4 on related approaches, because there are related approaches in which the initial condition will be crucial. The whole noise will be in the initial condition. In the diffusion, the whole noise is really given by the trajectory, by the various eta of t at various times. Eric, what did I say wrong? Yes. That's true. Exactly. Yes, yes. Thank you very much. This, okay, this is a mathematical statement. If you succeed in doing that, you're done. You have exactly the same probability for the forward and the backward process. What we have been doing is we use this very specific form of the forward and backward process, which are with the Ornstein-Uhlenbeck and the score, etc. And what you can find, what you can look at, is look at this formula, and you will find that it is valid only in an expansion at small dt. It's not, and then so that's why there is this, I was saying there is this whole part of the literature which does not necessarily go through Langevin, Fokker-Planck, or Ornstein-Uhlenbeck, but start really from that. And then what is really needed is to learn this kernel here. So you want to approximate this backward process with whatever the tools that you have, neural networks, etc., so that it will be as good as possible. And so if you look at the literature, you will find quite a lot of which is done like that. But I will not use myself this formalism here. As I said to you, there are many ways of looking at it. But I think that I like the good way, which is the way that I like. They are all good. I like my way. That's, no, I like to. I think it's good to have one way that you understand very well, because then you can connect to all the others. Okay. So discretization was a kind of a sidestep, mostly for those of you who really want to get into the literature. And yes. Now let us focus on the score. Because so far I have still not. Oh yes, maybe I should comment one thing. I don't know for you, but the first time I was told about this story of the backward diffusion generating an image of a cat from pure noise, I thought, what is that? That's black magic. The point is that when we use the backward diffusion formula, we have this score. So we use a Langevin equation, dx d tau, which is equal to x plus 2 times the score plus eta of tau. And the score is gradient of log of p at time tf minus tau. So the guy who is very important is this guy here, because there is no magic. Basically what you are encoding in the trajectory the full knowledge. I mean, at each time of the backward trajectory, you are at equilibrium. Equilibrium is not, well, you have the right distribution for that time, right distribution of blurred images. And so, and this is because you are using this gradient of log p. So when you go to very short time, well, when you go to very short time, what will happen is that this guy will concentrate you towards points which are distributed according to p0. But you are using a score which is a gradient of log of a probability distribution which becomes very close to p0 itself. So you are using the knowledge of something that you want to reach. So far, it's useless until now, what we have been doing. That you cannot generate new things from that. And so it will be very important to understand how to estimate the score. In the score, the p is the same backward and forward. Well, that's well. In my notation, this is a p forward. I use p forward t of x is equal to p backward t Okay, I have this correspondence. I mean, it's the same function. I'm just looking, it's a different indexation. I have my probability distribution, estimate it at time t, or I estimate it, so this is t, this is tau, and this is tf. But it's the same. Okay, so let us see how we can estimate this score. So what we have seen is that we have a probability distribution of x at time t, and it is equal to the convolution of A of P0 times a Gaussian distribution of x with mean A e to the minus t and variance delta t. And delta t is 1 minus e to the minus 2t. So it will be also interesting to look at the joint probability of A and x, the x being at time t. So now I'm looking at this joint probability. I have at time t, I have arrived at this point here. I started from that. I want to look at the joint probability of this and that. So what is it? The joint probability is just P0 of A times the Gaussian. So from this joint probability, we can deduce two conditional probabilities. I can deduce the conditional probability of x given A. That's easy. That is my Gaussian. It's a Gaussian distribution of mean A e to the minus t and variance delta t. Okay. And I can look at the probability distribution of A given x. And what is that? This will be equal to P0 of A times e to the minus x minus A e to the minus t squared over 2 delta t divided by square root of 2 pi delta t. I write it explicitly this time. And I have to include a partition function here. Okay. So I look at my joint probability. I divide by the probability of x. And so I will have, this will be my probability of A given x. So what is this object? This object is the following object. I have observed at a certain time t, I observe a point which is here. And I know that it has evolved from some initial probability distribution, maybe very complicated. Started from one point somewhere here and evolved like that. And the question is, when I measure this, what is my best guess from the starting point? So if I know P0, I know the arrival point. I can see the arrival point x as a noisy observation of my initial point. And so this conditional probability tells me, what is my best guess for the point where I started from, knowing two things, knowing a prior, which is my prior distribution P0, and an observation, which is that I have observed x here at time t. Okay? So that is just Bayes' formula. And it's interesting in itself that this is really seeing this whole process as a denoising process. You will often read in the literature that the whole structure of the backward process is denoising. And you can look at it. There are various ways of looking at it, but you can look at it as in the following sense, that you follow in your backward trajectory, you have less and less noise. You see when you follow tau, the signal is less and less noisy, and you want to find your best guess for the initial A. Okay, so this will be something that we will be quite interested in. By the way, what does it mean in terms of P0 of A? You know, P0 of A, I will start to go in models of P0 of A, which may be complicated statistical physics problems. P0 of A might be the one on which you have done your PhD. I don't know, the one on some variant of the Hopfield model with hierarchical correlation of the patterns, etc., etc. And you want to generate new ones, so you start to study the generative diffusion in that model. Your model, the one that you have been studying so far, it is in P0. And now, basically, what you could think of is, in terms of statistical physics, imagine that you have some configurations of P0 and you want to generate new ones. And you want to see if generative diffusion helps you to generate new ones. Well, then what you will have to do is study this backward process. And in some sense, what you are doing in the backward process is that each time you are looking at what is your estimate of the initial model given X. In particular, what you look at here is a kind of extension of your original model in which you have changed the measure and you have gone to something which is called the tilted measure. Here you have a tilted measure which is P0 of A times e to the minus A squared e to the minus 2t over delta t plus x dot A e to the minus t over delta t. So imagine, for instance, that you would your favored model has Ising spins. Okay, so P0 of A, it has binary variables. Okay. Then as soon as you start to do diffusion, you go to real space. You leave the space of Ising variables. But generative diffusion is smart enough that when you take it back to initial time, it will concentrate to xi, which is +1 or -1. So it will recreate the Ising measure. And you see that the way that x appears now, so A squared, if it is Ising spin, you can forget about it. This is just an external field. So this is just a measure that pushes the A measure in the direction of an external field, which is x. And of course, this x, the more you go to the backward measure, the more it concentrates on the right value, by definition of the backward process. So that is another way of looking at it. I will discuss that in the chapter 4. Okay, so back to the score. Sorry, it's a bit of a digression, but I will need them at some point. Yeah, let me just establish. So what is the score? The score is the gradient of log p. And if I look at this expression here, I can write it as 1 over p times the gradient of p, and the gradient of p is the integral over a, p0 of a times, well, when I take the derivative of that with respect to x, that's a Gaussian measure, e to the minus x minus a squared, etc. So I get a minus x minus a e to the minus t over delta t times e to the minus x minus a e to the minus t squared over 2 delta t normalized. So it tells me that the score is equal to minus x over delta t plus something that I can write e to the minus t over delta t times this integral p0 of a times the Gaussian, Well, what you see here is that this is precisely the expectation value of A with the conditional measure. So this is the expectation value of A given a time t and x, given that I have a process with a certain value of x and a certain value of t. This thing here is done with this measure here. As I write A T x okay, so this is nice. This is something which is very useful if you know P0 of A. That is, for theorists, we have gone some good way in the sense that if we know P0 of A, maybe again your favorite model, then you can start to study. You can start to study the tilted measure. You can start to study, can I get the expectation value of A with the tilted measure? If I am able to do that, I can monitor the backward process, and I can see if I can generate new data with my backward process. So theoretical analysis, this is good. Now, what we need is the next step, which I will do probably after the break, which will be to see how we can estimate the score. This was described by Eric already yesterday, but I will redo it with these notations here. How we can estimate the score from data, because here you cannot really do that from the data, and so we will see that formula after the break. Questions? Coffee. Coffee. Yes. I think it's certainly possible to do that. Then whether it is useful for practical situations, this is something that I just cannot guess. Yeah. The thing which is clear is that here I'm really describing, as I said, the simplest setup. If you have followed what I've done, I've done something which is also completely isotropic. I did not. I took exactly the same time step and the same schedule in various directions, etc. And depending on the structure of data, you can certainly adapt. That is clear. Whether there is data which needs adaptation going to Levy, possibly. I don't know. But it's at least it's a good exercise to redo it with what you say, putting eta as a Levy noise and deriving what is the new score. That's a good exercise for the break.